Hello everybody, welcome back. So today this video is a continuation of the previous video on basic derivative rules. This is part 2. In the previous one we talked about the constant rule, the constant multiple rule, and the derivative of x. In today's video I'll be talking about the power rule. And the power rule is one of the most common derivative rules that you'll run into. It's also one of the easiest to remember, so you've got that going for you. But let's say we wanted to find the slope of a graph of x to the n. So our function f of x equals x to the n. So the derivative of this function, f prime of x, is equal to, and we know from the limit definition of the derivative, is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So our f of x is x to the n. So for this part, we plug x plus delta x in for x in our original function. So we get that this is the limit as delta x approaches 0 of x plus delta x to the n minus x to the n all over delta x. Now in order to simplify this, we would need to expand this here out. So I'm just going to x approaches 0. I'm just going to write out what it is up here. So we have x to the n plus nx to the n minus 1 delta x plus n times n minus 1 times x to the n minus 2 times delta x squared. And this goes on until you end up with, at the end, delta x to the n. So all of this, and it keeps going on depending on how big your n is, minus x to the n all over delta x. Now I didn't write out this entire expansion, but I don't need to write out the entire expansion, and we'll see why in a minute. So this x here, x to the n, and we have negative x to the n, x to the n minus x to the n. These will cancel out. So we have the limit delta x approaches 0. And one more thing I'd like to do before writing it down here is we see that every remaining term has at least one delta x. So I'd like to factor this delta x out to the front. That leaves us with nx to the n minus 1 plus n times n minus 1 x to the n minus 2 delta x, on and on and on, until we get to plus delta x to the n minus 1 all over delta x, where I factored out the delta x to the front. Now we have a delta x on the top, or on the numerator and in the denominator. So we can cancel those. We get the limit as delta x approaches 0 of nx to the n minus 1 plus n times n minus 1 x to the n minus 2 delta x plus so on and so forth until we get to delta x to the n minus 1. So now we can directly substitute delta x, 0 in for delta x, so delta x goes to 0. This first term stays as nx to the n minus 1. This second term, since it has a delta x, goes to 0. All the other terms have delta x, so they go to 0. And this final term also has a delta x, and this goes to 0. So we can see from this that the derivative of x to the n is equal to nx to the n minus 1. So let me write that up here. So let's do a couple of example problems with this. So the first one that I'll do is one that I did with the limit definition of the derivative, and that is f of x is equal to x squared. So if we want to differentiate x squared, what we do in this nx to the n minus 1 is we multiply by the coefficient, or by the exponent. We multiply the coefficient by the exponent, and then we subtract 1 from the exponent. So what we'll do here is we multiply the coefficient, which in this case is 1, by the exponent. We get 2 times x to the 2 minus 1, which is equal to 2x, which is consistent with our result from the limit definition of the derivative. So let's do another example. Say f of x is equal to 3x squared this time. So we can say that the derivative of 3x squared is equal to, now there's a couple ways you can do this. The first way is you apply the constant multiple rule, which states that you can move a constant out to the front, and you get 3 times the derivative of x squared, which is 3 times 2x to the 2 minus 1, which is equal to 3 times 2x, which is equal to 6x. The other way is you could just multiply the coefficient by the exponent. So in this case, you multiply 3 by 2 to get 6, and then x to the n minus 1. In this case, n is 2, so 2 minus 1, which is equal to 6x. Now let's look at a slightly more complex function. Say f of x is equal to x cubed. So we take the derivative of this, derivative of x cubed. In this case, our n equals 3. So we multiply by 3. We get 3x to the 3 minus 1, which is equal to 3x squared. So now, that one was example 3. So this one's example 4. Say f of x is equal to 9x to the 10th. This here, x to the 10th, would not be fun to expand. We would have a lot of terms. I mean, you already have a good number of terms once you get up to 3. So 10 would be awful to try to expand. Unless you like doing that kind of thing, in which case, by all means, go ahead and do the limit definition if you want. Might take you a while and a lot of paper, but that's beside the point. So we know that this is the derivative of 9x to the 10th. So we multiply the coefficient by the exponent. So this becomes 9 times 10x to the n minus 1. In this case, n is 10. So to the 10 minus 1, 9 times 10 is 90. X to the 10 minus 1 is 8. So this, the derivative of 9x to the 10th, is 90x to the 9th. So that is the power rule. This is a rule that'll pop up again and again. You'll see it quite a bit. So it's a really good one to learn and to learn well. But I hope you enjoyed the video. If you have any questions, once again, leave them down in the comments below. And have a good day, everybody.